In a previous lecture, we focused on what happens when you introduce heat to a system or when a system loses heat. As a result, its internal energy will change, which is reflected in either its temperature change or the change in its state. But in general, this is not the only way to change the internal energy of a system, especially when it comes to gases. When you look at a gas, you have to also consider the change in its volume, because it's relatively simple, relatively easy to change the volume of a gas. It can expand or shrink sometimes, but many times its original volume. What happens when the volume of a gas changes from an energy perspective? Well, when the volume of the gas increases, the gas expands, it will push on the environment due to its pressure, and it does work to the environment. On the other hand, the environment can also give an extra force to the gas to shrink it, and therefore doing work on the gas. So it's not just heat going in and out of the system that can change the internal energy. You can also do work to it, or the system can do work to the environment that can also change the internal energy of a system. So now let's take a look at what happens when you consider work done on or by a thermodynamic system, especially an ideal gas, because it's the simplest system to study, remember? Okay, so here is a relatively simple way to find out the work done by the gas or on the gas. Suppose I have a cylinder of a uniform cross-section area A, and trapped inside is a gas of volume V and pressure P. Okay, now suppose I apply a force F to push down the cylinder. And as a result, there's a displacement of the cylinder dy, which in this case shrinks the volume of the gas. So you're compressing the gas. Okay. And as a result, we say that the gas has undergone what's called a thermodynamic process. A thermodynamic process. Okay. What's a thermodynamic process? Well, for a gas, I can depict the state of this gas on what's called a PV diagram, as you can see on the right side of this screen. Every point on this gas on the PV diagram is represented. It represents a certain state of the gas with a given pressure and a given volume. So there's a dot on a PV diagram that represents a state, and that dot can move, which means the pressure can change, the volume can change. Okay, so as the dot moves, the pressure and volume changes, then we say this gas is undergoing a thermodynamic process. Okay, as you can see, there's an example on the PV diagram. Here the gas starts from initial state, going to a final state. What happens to the volume? The volume shrinks, right? It goes from initial volume to the final volume this way. So the gas volume shrinks. And what happened to the pressure? Well, the pressure rises, right? The pressure rises from P initial to P final. So pressure rises. So that is a case when the gas is getting compressed and the pressure increases. That is the thermodynamic process. Okay. Now, one thing to be careful about this is that you have to do that slowly enough to allow the pressure to equalize within the chamber of the gas. That's very important, because there is only one value of pressure depicting every state of this gas. What if you do it so fast that there is not enough time for the pressure inside the gas to equalize? Then which value of pressure do I use? The one near the cylinder or the one near the bottom or anywhere else, right? It doesn't make any sense. You have to do it slowly enough so that the pressure is always the same everywhere inside this cylinder. And that is called a quasi-static process. Quasi-static. So that is an assumption for all thermodynamic processes, unless I tell you otherwise. Okay, I have to do it slowly enough. Quasi means almost. Okay? Quasi-static. It's not quite static, otherwise cannot move. Nothing will happen. Right? Nothing will change. So it's quasi-static. Right? So that's the condition. Now let's see what happens in this thermodynamic process as far as the work done is concerned. Different textbooks have different definitions for Q and for W. In our textbook, Q is always defined to be the work done, to be the heat gained or absorbed by the system. So Q is positive if the system absorbs heat, and it's negative if the system loses heat. And in our textbook, W is defined to be the work done on the gas. Okay, not the work done by the gas. They differ by negative sign. Okay, so let's look at, in this case, how much work is done by the on the gas as you push down a cylinder over a distance of dy. Okay, so the work done is force times displacement, right? F dy. Okay, that's the work done on the gas, dW. Now, the state of the gas is given by a pair of parameters P and V, but here I have F and dy, so I have to change F to replace by P and dy to replace by dV. So how do I do that? Well, for this cylinder, I'm pushing the cylinder down slowly. Remember, it's a quasi-static process, right? So if the cylinder travels so slowly, the velocity of the cylinder is very small, and therefore we say its acceleration is also very small. We can safely ignore it, especially if the cylinder travels down at a constant speed. The acceleration is actually 0, and that means the force pushing the cylinder down equals the force from the gas pushing the cylinder up. Right? Now the gas pushes the cylinder up with a pressure of P, and that P is spread out over the uniform cross-section area A, and therefore the force from the pressure of the gas pushing the cylinder up is P times A. And that should match F because the net force on the cylinder is 0. So therefore, F is equal to P times A. Okay, and then you have dy. Right? Now, Y is the height of the air column, of the gas column inside. So what is ADY? ADY really is the change in the volume. Except, don't forget, you have to attach a negative sign. Because you can see clearly in this case, the gas is being compressed, the volume actually decreases, right? So dV is actually negative, so be careful about that. But while dV is negative, the work done, dW, on the gas is positive, right? So dW is positive, and dV is negative. The way to balance that is to attach a negative sign in front of PdV. So both sides, in this case, are positive. This is the work done by the cylinder as it pushes down by distance dy. Okay. In general, how much is work done on the gas when it goes all the way from a certain initial volume to the certain final volume? So you're looking for W, not dW anymore. So you have to integrate both sides. Okay. So W equals what? The integral of dW. So you have to integrate P dV with a negative sign. And the volume increases from V initial to V final. So this is the expression of the work done by the environment on the gas as the volume changes from V initial to V final. Don't forget this negative sign. And what that, again, physically what that means is that as the gas volume shrinks, so dV is negative, the environment does positive work. And as the dV is positive, so the gas expands, then the gas does positive work, but the work done on the gas by the environment is negative. Okay, so this is an important formula for the work done by the gas, on the gas, but you be careful about this P here. P is not necessarily a constant. As you can see from this example here, P increases. Okay, how does P change as a function of V? That depends on what kind of process, what kind of thermodynamic process it is. It can change, it can be different. Okay, so that's a general formula. Now, let's look at the next topic. Actually, the main topic of this lecture, and that is so-called the first law of thermodynamics. Okay, let me add the first law. The first law of thermodynamics. So we have studied two ways to change the internal energy of a thermodynamic system, especially a gas. One is to give it some heat. The second is to do some work. Okay, you can do work or give it some heat. Either way, you can change. You can change the internal energy of a system. So what is delta E internal heat? Well, in the previous lecture, we learned how to change it by giving it some heat, Q. Again, this heat Q is defined as positive if heat is being absorbed by the system, okay? But now we learned there is another way to change the internal energy is by doing work on the system. So plus the work done on it, W, okay? This is a more generalized version of the conservation of energy. We have seen conservation of mechanical energy, right, involving only work done by conservative forces. But when there's friction happening, the situation is different. Energy in a mechanical form alone is no longer conserved. But think about it. If you have friction doing work, you're rubbing something, you did work, that work doesn't seem to change the mechanical energy, right? If you step on a brake of a car, all the kinetic energy eventually is gone. You didn't gain any kinetic energy. So what happened? Where did it go? Well, it's because friction did negative work, right? So the kinetic energy disappears. But as a result, the brake pads actually heat up, right? The road can also heat up a little bit. So some thermal energy has been created. So there's heat involved. So if you look at energy in all forms, not just limited to mechanical forms, then everything is accountable. Energy is always conserved if you include all of its forms, not just mechanical form. Okay, the conservation of energy in the most general form is not limited to mechanical energy. When there's heat involved, it is called the first law of thermodynamics. So the first law of thermodynamics is really nothing fundamentally new. It is the restatement of the conservation of energy involving thermal form, in addition to work that we studied in mechanical processes only. Okay, so again, what this formula tells us is there are two ways to change the internal energy of a system. You either heat it up, give it some heat, or you do some work to it. By the way, Q and W can both be negative. If heat is lost, then Q is negative. If work is done by the gas, as the gas expands, then W can be negative. Okay, so be careful about that. Now, so let me box that. That is the first law of thermodynamics. Okay, very important, one of the most fundamental principles of nature. All right. So let's see here. What we're going to do now is we're going to apply the first law of thermodynamics to study certain processes involving ideal gas. Okay, there's some special cases that we are going to apply the first law to. The first case is a very generalized case, even though it's still special because there's some feature about it. It's a cyclic process, okay? A cyclic process, one of the most important special cases, which is actually still quite general. And that is, you start from a certain point on a PV diagram, which represents a certain initial state, whatever that is, say that, and you undergo a certain process, but you come back to yourself. Okay, you come back to yourself. So it's a self-enclosed loop of any shape. Okay, we can apply the first law of thermodynamics to this process. And as you come back to yourself, what is the net change in your internal energy? Now remember, internal energy is basically all the energies at the molecular and atomic level, you add them all together, right? If you return to your original state, what happened to the internal energy? Well, internal energy is a function of state. If you have a certain pressure, certain volume, certain temperature, that means you have a certain amount of internal energy. Okay, now after the cyclic process, you regained all the initial parameter, P, V, T, and so on. Therefore, there is no net change in your internal energy. So delta E internal is what? Is 0. Okay, is 0. What about W and Q? Well, W is interesting. It really depends on whether this process happens clockwise or counterclockwise on the PV diagram. Let's see here. Let's see why I say that. Well, if you have a let's draw a PV diagram, okay? Let's say initially, look at a PV diagram. It doesn't, the process is not a self-enclosed process for now, okay? So we are going to go from initial state to a final state. You know, let's say we go like this, okay? So here is your initial state, and here's the final state. Okay, it goes this way. How much work is done? Well, the work done by the gas, I'm sorry, on the gas, dW equals negative PdV. But what is P times dV anyway? You look at a infinitesimally small step of on a PV diagram, okay? A small step. From this point to that point, okay? The volume changes by dV, and the pressure is P. Right? Pressure is P. So what is PdV? PdV isn't it just this area here? Okay? So this area under the PV curve represents what? PdV. So what is the integral? What is the overall amount of work done on the gas? You have to integrate over that, initial to final, okay? Initial to final. And that's W. So W is what? Is the area under the entire curve. This entire area. That is the work done, PdV. Don't forget a negative sign, okay? So what you're getting here, this area, is the work done by the gas if you do not include this negative sign. If you include this negative sign, then the work done on the gas, W, as we define in our notation, is this area under the curve with a negative sign. Okay, so once we understand this, then look at this cyclic process here. How much work is done on the gas as you complete the cyclic process? Counterclockwise, the way I draw it, counterclockwise. Let's see. The area between this point and that point, as it goes this way, as it goes this way. Okay, let me use a different color. As it goes this way, from here to there. You have this area, don't you? You have this area. Okay, what does this area represent? It's the work done by the gas as it expands between here and there, right? And that's the work done by the gas. Now, later on, the gas shrinks between here and there. It shrinks all the way to here. And then during that process, the work is done on the gas, right? And how much is the work done on the gas? Is the area, it's a bigger area under that curve. It's this bigger area under that curve, right? So how much is the total work done on the gas for the entire process? You have to take this bigger area, you know, the yellow area, minus what? Minus a smaller area, and that's when work is done by the gas. That smaller area as the gas expands. What do you get? What's the net? The net is the area that's enclosed by the PV diagram. Okay, so I'm gonna use a third color now. It's the area enclosed by the PV diagram. It's going to be this orange area. This orange area is the work done on the gas for this process if it moves counterclockwise. Okay, so when the process happens when the cyclic process happens counterclockwise, a net amount of work is done on the gas, and that equals to the area of the enclosure by the PV diagram. W, that's W right here. W. Okay, this self-enclosed area. And that is because as the gas expands, it doesn't work to the environment, but the environment does more work to it as the gas shrinks. Okay. What if the process happens clockwise? Then everything is reversed, right? The gas does more work as it expands, and the environment does less work to it as it shrinks. And therefore, overall, the work done by the gas is greater than the work done on the gas. And this self-enclosed area still represents work, but it's the work done by the gas. Or we can say the work done on the gas overall is negative, whose magnitude equals to the area of the enclosure on the PV diagram. Okay, so if you apply the first law of thermodynamics to the process, then you have 0, which is delta T internal, equals Q plus W. And then when W is positive, Q's got to be negative, and so on. Okay, so in the example that I drew, a counterclockwise process, a certain amount of work is done on the gas, so Q, so W is positive in this case, so which means Q must be negative, which means what? The gas must give up heat to the environment, okay, to stay unchanged in its internal energy. So basically, let's look at some numeric example. Let's say in this process, the gas went through a cycle, and there's no net change in internal energy. That is because the gas, somebody did 100 joules of work to the gas, but the gas lost 100 joules of work to the environment, and therefore overall the energy doesn't change. Okay, if the gas undergoes this process in a clockwise pattern, then the gas does work to the environment, and therefore it has to absorb some heat to keep the internal energy unchanged. All right, so that's a cyclic process. Another special case is what's called an isothermal process. Isothermal here means the temperature remains the same. Okay, now on a PV diagram, what happens when the temperature remains the same? What kind of plot is this? Well, we can use the ideal gas law with a constant pressure, with constant temperature. PV equals nRT, nRT, and that's a constant because T is a constant. Yeah. So for an isothermal process, P times V equals a constant, which is nRT, and that is a hyperbola, isn't it? Right? It's like x times y equals a constant. Then you plot y versus x, you get a hyperbola, which is what you see here. Okay, so in this case, I have an isothermal expansion because V initial is less than V final. In an expansion process, the work done on the gas is negative, right? So how much is it equal to? W. How much is it? Negative PdV initial to final. That's a generic formula, but in this case, P equals nRT over V. I mean, P is always equal to nRT over V, but I'm writing it down this way, especially useful here because T is a constant, so I can take that nRT, all these are constant, take them all out, then you can finish this integral. It's 1 over V dV, see here? I to F. I can only take T out because it's an isothermal process, T doesn't change. Okay, so that gives me a natural log function, doesn't nRT, natural log of V final over V initial. Now, right. Now, you know the natural log function, if the argument is greater than 1, then the entire log function is positive. Otherwise, if the argument is between 0 and 1, then the log function is negative. So this is greater than, this is greater than 0 if V initial is greater than V final. Okay, when V initial is greater than V final, the argument the log function is less than 1, the log function is negative with another negative sign in front of it, W is positive. And that makes sense because V initial is greater than V final, looking at a compression. For compression, W, the work done by the environment, is positive. But if V initial is less than V final, they're looking at a thermal isothermal expansion, then the work done by the environment is positive, as you can see from the work done by the gas is positive and the work done by the environment is negative. Okay, because mathematically you see the log function is positive, but there's an actual negative sign in front of the expression for W. Okay, and so in an isothermal expansion, you look at the ideal gas law. I mean, you look at the first law of thermodynamics applied to it. Delta T internal equals to Q plus W. I know how to calculate W, is right there. But what's the sign of Q? Is it positive, negative? Well, to understand that, we have to understand what happens to the internal energy when the temperature does not change. Okay, this involves a little bit of microscopic understanding, but it's not that hard to comprehend. Again, the internal energy is the sum of kinetic and potential energies at the molecular level, right? If we give something some extra amount of heat, as we saw in calorimetry, the temperature will increase, which means the molecular energy will increase as the temperature goes up. But here the temperature doesn't change, which means there's no change in the molecular energy in the kinetic form. Now the potential form doesn't change either, because the potential form depends on what kind of state it is, whether it's gas or liquid, or, I mean, in this case, there is no phase change. So therefore, here's something very important. When the temperature does not change, okay, if T stays a constant, then E internal is also a constant. This is unique for the isothermal process. Every step of the way, there is no change in the internal energy of the system. This only happens in isothermal process. Okay, every step of the way. Of course, you come back to yourself throughout whatever process, there is no net change in terms of energy, but here, there's no change into energy every step of the way. Okay, so then I have 0 equals Q plus W in this case. So in an isothermal expansion, W is negative, so Q is positive, which means as the gas expands, it does work to the environment. So how come the energy doesn't change? Because the environment gives it some heat. Okay, in isothermal compression, somebody does work to the gas, but how come its internal energy doesn't increase? It's because it gives us some heat to the environment. Okay, so Q equals negative W. So I know the expression for W, therefore I know the expression for Q as well. It is equal to nRT, natural log, V final over V initial. It's just the opposite of W. Okay, so that's a special case, isothermal process. Okay, now let's look at yet another special case, isobaric process. Isobaric process. What's an isobaric process? Okay, that is when the pressure, that's when the pressure stays a constant. You can see on this diagram here, right? The pressure stays a constant as it goes from initial to final state. Now, the way it's depicted, the pressure actually is, when the pressure stays a constant, the gas is undergoing an expansion. It doesn't have to, but here in our depiction, V initial is greater than V final, so it expands. Now, as it expands, remember PV equals nRT. That's always true for any process. P doesn't change, but V increases, and therefore T increases, right? So it goes from initial to final, increasing its temperature from T1 to T2. So T2 is greater than T1. We can say the initial state lies on an isotherm, which is this blue line right here. This blue line is called an isotherm at temperature T1. It goes up to a final isotherm, to a point on a final isotherm at temperature T2, and T1 is less than T2. Okay, so that's something we keep in mind for this particular depiction. I want to apply the first law of thermodynamics to that process and see what happens. First of all, the work done on the gas is very easy to calculate in this case, W. Why? Because the pressure doesn't change. Okay, so W equals negative PdV from V initial to V final But P is a constant. I can take a P out, negative P, V initial, V final, dV. And then it's just equal to negative P times V final minus V initial. So as long as V final is greater than V initial, W is negative, which means, makes sense, right? The thing, the gas expands at a constant pressure, it pushes the environment on its way, and therefore it does work to the environment does negative work to it, okay? If it shrinks, then W is positive. Now, if you apply the conservation of energy, or the first law of thermodynamics to this process, what happens? Delta T internal equals Q plus W. So in the picture, to pick it to the right, to the left, W is negative. Okay? W is negative. But delta T internal is a positive or negative. Well, delta T internal is positive if the temperature increases, right? If the temperature stays the same, it doesn't change. When temperature decreases, it's negative. So in this case, the temperature increased from T1 to T2. So the internal energy increased. And the way to make it work is Q has to be greater than 0. Okay, so from a first law point of view, this isobaric expansion, you have a case where the gas expanded, the gas did work to the environment did negative work to it. If nothing else happens, you can expect a decrease in internal energy of the gas. And yet, in reality, the gas actually increases its kinetic energy, the internal energy. And the reason why that happens is because it absorbs some heat along the process, along the way. The heat absorbed is greater in magnitude than the work done by the gas. Okay, for example, if the gas did 10 joules of work to the environment, but it receives 30 joules of heat from the surrounding, then overall its internal energy will increase by 20 joules. Okay, so that's an isobaric process. Now, let's look at yet another example. Isometric process. Isometric, sometimes we write it as isovolumetric, which means the volume is a constant. The volume is a constant. It's just like, what happened to a solid or liquid, right? The volume hardly changes. What is the work done in this case? Well, that's as simple as it gets. It's just 0. Why? Because dV equals 0. Look, I'm still going to write it down. Okay. Negative P dV. V initial equals 0. But that equals 0 because V initial equals V final. Okay, so just 0. Then you apply the first law of thermodynamics to this process, then you get delta T internal simply equals Q plus W, but W equals 0, so it's equal to Q. Okay, so does the internal energy change? Yeah, it does. And the amount of change equals to the heat it absorbs because there's no work involved. In the way depicted on the left side of the screen here, you have an isometric process in which the pressure increased. Okay, so you don't change the volume, but somehow you see a pressure increase. What do you think happens to temperature? The temperature must increase, right? You heat it up, temperature goes up, the pressure rises, right? When you heat it up, you have to give it some heat. So in this case, Q is positive, delta T internal is positive. You can also have a situation where you seal a tank of gas so the volume doesn't change, but the pressure decreased. That's because the gas cools down, right? So the pressure decreased. As it cools down, it gives up heat to the environment. So Q is negative, as is delta T internal. Okay, so that's another special case. Now, I'm going to take a look at the last special case, which is perhaps the most interesting one we'll be studying so far in this lecture. It's called an adiabatic process. Okay, adiabatic process. This is the most interesting because I'm going to think about an example to illustrate with you the feature of this curve using the first law of thermodynamics as a guideline. So what is an adiabatic process? This term adiabatic here means that there is no heat exchange between the system and the environment. So we can think of a case where the system is well insulated, okay? you can change its volume, you can do work to it, but you do not allow it to exchange heat with the environment. Then we say it's what's called an adiabatic process. So Q equals 0. Now, you will learn in a later chapter that for an adiabatic process, in addition to the ideal gas law, you also have a special rule that satisfies, and that is P times V to the power gamma equals a constant. What is that gamma equal to? You will see in the next chapter. But for now, I can show you one thing about this gamma. Gamma is a number that has to be greater than 1. It cannot be 0.5, for example. I don't know if it's 2 or 3, but it cannot be 0.5. Okay, why is gamma greater than 1? Can we see that from the first law of thermodynamics? Well, that is what I want to discuss with you. First of all, let's consider a case where you start from a certain initial state, I, undergoing an isothermal process. So the temperature stays at T1, okay? That's this blue curve that you see here. Now, let's say we start from the same initial state I, but this time I'm undergoing an adiabatic process, okay, which is Q equal to 0. Q equal to 0. Start from the same point here, I. You know, for the isothermal process, P times V equals a constant, right? But for an adiabatic process, P times V to the power gamma equals a constant. If gamma is greater than 1, that means the effective volume change will be more dramatic than when gamma is equal to 1. Which means if gamma is greater than 1, and as it expands, so V increases, you should expect a faster decrease in its pressure, which means the PV curve for adiabatic line would be below that. Because as gas expands, the pressure has to decrease faster because gamma is greater than 1. But let's assume that's not the case. Let's assume gamma is less than 1. Okay, so the effect of volume expansion is less than the case for isothermal, which means I would expect a curve like this, right? Will be above the isothermal line. Now, I want to show that this is just not possible because it violates the first law of thermodynamics. Okay, so therefore, gamma has to be greater than 1. Okay, let's see how we show that. Let's assume that this is the correct way. So you have this adiabatic expansion, which is the line above that thermal line. And let's do this. Let's keep on going. Let's keep on doing adiabatic expansion until I reach a point, this point right here, which is the same volume of the isothermal expansion which I previously did. Same volume. I can always stop expanding, which reach that point. And now I'm going to take a turn. I'm going to use a different color. I'm going to take a turn and move down to here. So I have 3 segments. 1, 2, and 3. Suppose this time I do a cyclic process, starting from initial point at the top. Okay, step number 1. Step number 1, I'm going to use a number to indicate the first process, step number 1. That is Q equal to 0. Okay, it's an adiabatic process. And step number 2 is delta V equal to 0, because I made this point and that point to have the same exact volume. Okay, same exact volume, same exact. And the third step is an isothermal contraction or compression here. Okay, going backwards from higher volume, from a greater volume to a smaller volume. This is a cyclic process. Okay, I can always construct a cyclic process like this. Now, in the cyclic process, I'm going to apply the first law to the cyclic process. And I want to show you that when you do so, you will find a problem. That is, you cannot make that happen. It violates the first law of thermodynamics. How? Let's see. For the entire process, I understand that I have delta E internal equal to 0. because this is a cyclic process. So delta E internal equals Q plus W, and that equals 0. It's a cyclic process. Okay, cyclic process goes back to the same initial state. Now, for the entire process, it's actually made of 3 steps. Step 1, step 2, step 3. So that tells me that Q1 plus Q2 plus Q3, that equals Q. And then plus W1, W2, and W3, add them all together, you should get 0, right? Q1 is the heat absorbed in the first step, Q2 is the heat absorbed in the second step, and so on. W is the work done on the gas in the first step, and so on. Now let's see what happens. Let's see what happens to Q1, Q2, Q3, W1, W2, and W3. Q1 is 0. How do we know that? Because it's an adiabatic process. Okay. Okay, so Q1 equals 0. What about Q2? Q2 is the heat absorbed by the gas as it goes from this point to that point. Okay, remember, this is an isometric process. No work is done. Right? So does the gas absorb heat or receive heat? That all depends on what happens to its energy. Now, it starts from this point. This point obviously has, this point. This point obviously has higher temperature than that point. Why? Because they have the same volume, okay? But the first step right here has greater pressure than that. Since PV equals nRT, that's valid for any process, right? I'm going to write down this again. PV equals nRT. So you compare here with there, they have the same V, but the final step, the final process, which is final point, which is right here, has greater, has smaller volume. Therefore, it's got to have, it's not smaller, same volume, okay, same volume, but smaller pressure, right? So it's got to have lower T, which means for the second step, okay, the temperature went down. When the temperature went down, it lost internal energy due to the second step. So it's lost internal energy, it must have lost some heat because no work is involved. So Q2 is less than 0. Okay, it gave us some heat. Now look at step number 3 here. That's an isothermal compression. So in isothermal compression, there is no change in internal energy, and yet the gas gets compressed, so somebody did work on the gas, right? So it must give up some heat. So Q3 is also less than 0, right? And we studied all these cases before individually. So for the Q, Q1 is 0, Q2 and Q3 are both negative. So overall, this Q is less than 0. So the entire process, heat is being released by the system, not absorbed. All right. Now let's look at W1, W2, and W3. W1, W2, W3. If you add them all together, don't you get the total work done on the system? And that equals what? Equals to the enclosed area with a negative sign, right? You go back to what we studied before, cyclic process, right? We studied that, okay? So in this process is done clockwise. The way I drew it, it's clockwise. So the gas does overall positive work to the environment, and therefore the environment does negative work to the gas as a whole. So this whole thing here, W is negative. Now we have a problem, don't we? Look at the left-hand side of the last equation. Q is less than 0, W is less than 0, but when you add Q and W, what do you get? You get 0, don't you? This is crazy. You get 0. That's what the first law of thermodynamics says. That doesn't work, right? A negative number cannot be equal to 0. So therefore, this entire process cannot happen because it violates the first law of thermodynamics. And what was the assumption that we made? The assumption we made was that the adiabatic line lies above the isothermal line, which corresponds mathematically to gamma less than 1. So gamma cannot be less than 1 without violating the first law of thermodynamics, right? So that's an example of analysis with the first law of thermodynamics. And you will see in the next chapter what gamma really equals to. Interestingly enough, it has to do with molecular structure of this gas, but it's never less than 1. You will see explicitly what that equals to.